Okay, so today we are going to be talking about the control unit specifically. A couple of announcements before we get started. So your exam 1 was conducted during last class day. The exam is getting graded right now, and we are planning to return that to you by Monday. So exam 1 will be graded by Monday, March 8th. So during class on March 8th, I will be showing you guys the distribution of exam 1 scores. I'll talk about the average and if there are any concerns, we can talk about that on Monday. And then I will tell you guys what the regrade policy is for exam 1. So in the last class, we were talking about data path. Today, we are going to turn our focus on the control unit. So this is the complete data path, single cycle data path that you guys have been seeing. So this is a recall of a previous, the block diagram from a previous lecture. You've got the instruction memory over here, the register file in the middle, ALU, data memory, and a lot of other combinational circuits. For example, you have 2:1 muxes, several of them. You've got the sign extender module. You've got a shifter in order to compute the byte address by shifting it left by 2. That's equivalent to multiplying things by 4. So you've seen all of this in the previous data path lecture. What we are going to do is talk about what this is lacking, right? This was specifically constructed for about 8 instructions. There was add, there was load word, there was store word, there was branch when equal, and then there was a jump instruction which we didn't talk about. So first we are going to try to add the jump instruction, and then we are going to see if this can be applicable for all MIPS instructions. So first things first, let's try to add the jump instruction to that data path. And this is by simply adding a shifter, right? So for a jump instruction, all we are doing is we are adding this shift left by 2 address, shift left by 2 component that takes in a 26-bit address, shifts it left by 2 bits, padding it with zeros on the right, computes the 28-bit address, and then it also gets 4 bits, 4 most significant bits of PC plus 4. So PC is current instruction, the jump instruction, and PC plus 4 would be pointing to the next instruction. So what it would do is it would take the first 4 bits, the 4 most significant bits of, this is 4 MSBs, 4 most significant bits of PC plus 4, and it would need to, so you got 4 most significant over there, and then 28 least significant bits coming from the output of the shifter, and that's how you would compute the 32-bit jump address. So this is specifically for the J instruction, right? Jump instruction. But now, we need to also add one more line. For example, for jump instruction, you have an output coming from the control unit going into the MUX as the select line. So that'll help you to pick up either this path, which is the jump address path, so that you can execute that, or the one that you computed earlier, right? So earlier you had an option to select one from PC plus 4, or for example, if you were doing this for load word or store word instruction where you have to add the 16-bit offset address to a base address, then you would get that on the second path. So you pick one of those first, depending on the control that is coming from an AND gate. The inputs to the AND gate are branch, are you branching or not? and also the zero result. For example, if you are trying to do a branch when equal, you would subtract the two registers, and if that is a zero, that line would be asserted. And if the branch instruction is high and the zero result is true, then you would pick the ALU result from here. Otherwise, you would do PC plus 4. And then the second layer of selection is between what you selected earlier and whether you have a jump instruction or not. So that's how we are adding the jump instruction to this. So all we added was 1 shift by 2 and 2:1 mux. Everything else remains as is. But now that we have started talking about the outputs such as jump and branch, where are they coming from? Well, they are coming from a control unit. And this control unit is getting inputs from the 6 most significant bits of the instruction. What are those? Those are for the opcode, op field, right? For any type of the instruction, whether it be R, I, or J, the 6 most significant bits are going to be your opcode. So the main control unit, this is the main control unit. I need to differentiate that because there is also an ALU control. The main control unit would look at these 6 bits and then appropriately assert or not many of these control signals. For example, there is a register destination, which is to pick up one out of RT or RD, right? So the second field or the third field to talk about which register things are being written to, right? So depending on the type of instruction, in one case it is the RD, in the other case, for example, for the load word case, it would be coming from here. So again, depends on the instruction, you would have the register destination to pick this guy or this guy. So that's going to the input of this particular mux. Then there is the jump. Okay, so that's going to the other 2:1 mux that we talked about. The branch instruction going to the AND gate to compare that being true or not and the zero result being true or not coming from the ALU. Memory read and memory write, though, where is memory write? Memory write, right here. So memory read and memory write, those are going to, memory read and memory write are going to the memory, right, for read and write access. So are you writing to memory or are you reading from memory? Whether you're doing a load word or you're doing a store word. There is memory to register. So for example, after you read some data from the memory, suppose you're trying to write this into a register, right? So that would happen if you were loading a word from memory to a register. So you would then, in that case, you would pick up this path. So the mux control would need to be 1, versus if you were, suppose, doing an add instruction in which you would never have to do a memory access. What you would do is you would take the result of that add addition operation, and then you would let it bypass the memory and then write it into the register file. So that register, the memory to register is to pick up one or the other. I can also highlight that in, say, blue. This guy is for here. Now let's talk about register write. The register write signal is simply going to control whether you are writing to a register in the register file or not, right? So that's something that we have looked at earlier. There is also ALU source. So ALU source, again, that's a 1-bit control to pick up the operand. Is the operand is one of the operands to the ALU coming from the register file, or is it coming from the 32-bit sign extended value? Now that depends again on the instruction, right? So for example, if you're doing an add, then you're reading from there. If you're doing, for example, a store word or load word, you would be taking the 32-bit assign extended address, and then you would be adding it to the base address that is coming from the register data 1, read data 1. So that would be ALU source. Which is it? Is it read data 2 or is it the 32-bit extended? Now, we have talked about that. We have also talked about register destination. We have talked about jump. We have talked about drawing. Now let's talk about ALU op. There's a new field which is not 1 bit. Let's focus our attention over there. So where is that going to? Let me track that. So ALU op is coming from the control, main control, and it is actually going into a new control unit called the ALU control. So this is to essentially parse out specific instructions for the ALU. Now look at this ALU control. It is getting two inputs. One is from the main control, which is, we will see examples in which that will be 2 bits. And it is also getting 6 bits from the instruction itself. What is in that field? Well, it depends on the type of instruction. So if it were a R-type instruction, what would you get from the 6 least significant bits of that instruction? Anyone? We know that the R-type instruction format starts with the opcode, then you have RS, RT, RD, shift amount, and then the last 6 bits are for function code, right? So this is the function code here. FUNCT, I think it's short for, in the MIPS reference card. So the ALU control is giving an output that goes to the ALU to tell it what exactly to do, which operation to perform, but it is getting controls from the main control unit called ALU Op, as well as the 6 bits from the instruction itself. Those are the 6 least significant bits, right? So let's also write 6 LSBs. Now, of course, this is for R-type instruction. If it were a I-type instruction or a J-type instruction, those 6 bits would be part of the 16-bit immediate or part of the jump address, right? So those would not mean anything at that point. It is only for the R-type instructions that this would make sense. And then, so we have added on 2 control units. One is main and the other is ALU. The main control unit is getting 6 bits from the op field, which right away tells you what operation and all that. So it's a note that the op field is present for all 3 types of instructions, but the function field is only present for the R-type instructions. So depending on which one you're operating, these will be relevant. For all instructions, that will be relevant. All right, questions about things that we have discussed here? So plenty of things that are carrying over from the data path, but now we are adding 2 control units. One we are calling the main control, the other we are calling the ALU control. Our goal in this lecture will be to figure out what goes here and what goes here and how they are determined, because we need to send out appropriate controls for the type of instruction that we are trying to execute. Questions here? All right, let's move on. Now let's talk about the control signals that are coming out of the main control unit, right? So I can say this is outputs of main control. So there is register destination, register write, ALU source, and all that. So these are all of them, but not all of them. Most of these guys over here. So what is their purpose? So let's talk about a few of them. Other things are sort of repetitive from the data path. So register destination, what is that? What is the effect when it is not asserted? What is the effect when it is asserted? So when the register destination is not asserted, what does that mean? That means that this guy is not asserted. That means that this is 0, right? So if this is 0, the write register we are picking up is actually what we give in the RT field. Right? If it was asserted, then we would be using it for the RD, which is meaningful for an R-type instruction. So that's what you see over here. Register destination number for write register comes from the RT field versus the RD field. Register write. When it is not asserted, then the effect is none. When it is asserted, then we are writing to a register in the register file with what? With the value that is on the write data input. So that is with reference to register write that is highlighted in pink over here, that goes along with the write data that you want to be available on that line. Again, that is a 32-bit line, right? Because it's a 32-bit data that you would want to write to one register, because registers are 32-bit. All right, ALU source. Again, this is a MUX control over here. Where is ALU source? ALU source is right there. So when it is not asserted, what would be the effect? And when it is asserted, what would be the effect? When ALU source is not asserted, one of the operands that goes into the ALU is the read data to. That's your second register, read register to, the contents of read register to. And when it is asserted, it would be the 32-bit sign extended offset or immediate. It could be an offset, it could be an immediate, depending on whether it's a branch operation or it's a add I, like immediate arithmetic operation. So that you see over here, right? So if it is not asserted, then you're using one of the ALU operands to be read data to. When it is asserted, then it will be the lower 16 bits of the instruction, which is the sign extended instruction. So all those details are listed over here. Let me talk about a couple of them here. Memory read and memory write. When they are not asserted, then the effect is none. However, when they are asserted, then you are either reading from memory. Why would you need to read from memory? Well, you may have a load word, right? When you do a load word instruction, then you are reading from memory. And when you do a store word instruction, then you are writing to memory. So in load word, you are moving data from memory to the register, and you would need to assert memory read. But if it is not asserted, then the effect is none. And similarly for memory write, that is used to write data into the memory. For example, while the store word instruction is being executed, not asserted, effect none. When it is asserted, you will be able to write to the memory. Depending on what you provide, what will be written? Well, it will be whatever you have on this line over here, write data. All right, let's talk about something else. PC source. So that is, where is my next instruction coming from? Is it coming from PC plus 4 when it is not asserted, or is it coming from the branch target address? So that is computed by adding the base address in a register to the offset address provided as part of the I-type instruction. So that's your PC source. Where is the new PC going to come from? And that is the 1-bit control for this particular MUX, right? Sorry, not that MUX. The PC source is here. This is jump. Oh, the PC source is not shown over here, but it is coming from here. Next, memory to register. In the case of memory to register, this is sort of the last control at the output of the memory unit. When it is not asserted, what happens? When it is asserted, what happens? Let's take a look at this particular diagram to understand that. When the memory to register is asserted, then whatever data comes out of the memory is going into the register file or the right data input. And if it is not asserted, then you are taking the output of the ALU and passing it across to be able to write to the register file. So in one, you are passing whatever you read. In the other, you are passing whatever you computed by the ALU. So can you guys think of two instructions in which, while executing which, you would be going like that, asserting ALU's a memory to register? Can you guys think of a instruction there where you would need load? Okay, so load word, you would need it, right? So for example, load word, you are trying to move the data to a register. So load word would be an appropriate example there. How about ALU result? The output of the ALU result needs to go into the register file. When add I. So add I will do it. Yep. Add will do it. Yep. So all your arithmetic operations will fall in this category because there are only two instructions that need memory access: load word, store word. And in store word, you don't need to read it; you only need to write it. Okay, so it looks like you guys are picking up what I'm putting down, so that's good. All right, questions here? Is there ever a case where memory read and memory write are both active? So if no, there is not a case where you have both active at the same time. That cannot happen because we are looking at a single cycle data path, right? You're saying that only one instruction is being carried out in one cycle. So that's not going to happen. Although I should say this, that this none and this none essentially means that you don't care what the value is, right? If you're not doing a load word or store word, these controls don't matter. But definitely both cannot be active at one time. And somebody needs to take charge of that, right? Somebody needs to make sure that that never happens. So who do you think will take charge of that? Who do you think, which component over here will make sure that both are never active at the same time? Main control, yes, absolutely. The main control looks at the op field and it gives out the memory read and memory write cannot be active. Both cannot be active at the same time. So the control unit takes care of that. All right, let's move on here. Now let's talk more about adding control. So what are you trying to do? You're selecting the operations to perform, right? Are you doing ALU? Are you reading or writing memory? And so on. So there are plenty of operations to perform which you are adding control to your data path. The control of flow of data. So by selecting appropriate multiplexer select lines, by asserting them or not asserting them, you are essentially controlling how the data flows through that data path along all the components. So that those select lines would need to be controlled using the main control unit. Information comes. Where is the information going to come from? Like what controls, right? The instruction itself is going to have fields that will allow that control unit to operate on. In other words, the input to those control units is coming from the instruction itself. So if you look at a 32-bit instruction, for example, over here, this is an add instruction, an R-type instruction in which you are adding the contents of register number 17 and 18, and you are putting the result into a register, destination register number 8. So what is the 32-bit instruction format for this? You have the first 6 bits to be the opcode. They are all zeros for the add instruction. Then you have RS, RT, RD. We can quickly highlight these. So this is, say, blue, and blue is the destination. So that's go over here. That's 8. Then this is your RS. That would go over here. And then this is your RD. RT, sorry. That's your 18 right there. Then you have the shift amount. We are not doing any shifting over here. And the last 6 bits are for the function field for add. Why do you need this for add? Well, because you can have variations of add. You can have add unsigned, for example. So you need that function field. So what that means is this is going to increase the variations that you can have on a specific R-type add operation, right? So that's what the function field is used for. And we saw that this op field is sort of going directly into the main control unit, right? That is becoming the input of the main control unit. However, the function field, the last 6 bits, only for the R-type instruction, because there's no function field for the I and the J. The last 6 bits are an input to the ALU control. But the ALU control also has 2 additional inputs. So I should also probably mention that. This has ALU control. ALU control also has ALU Op. But that ALU Op is actually coming from the main control unit, right? So if you think about the ALU control, this guy right here, it is getting the 6 bits from here as an input, but it is also getting 2 more bits from the main control, ALU Op. All right, so let's move on here and take a look at the two units, right? So the control unit is a combinational circuit. There is no memory involved in that. Things are always going to move from one to the other end. So input, take a look at the input and then determine what are the outputs. Take a look at this, the input here and the input here, and then figure out what is the output over here. So the inputs are directly, the combination of the inputs is directly impacting what is the output. There is no sequential element to this. There's no memory to this, the 2 units over here and here. Organized into 2 parts, main control unit and the ALU control unit. So we've been talking about that. Let's see, let's move on here. So before I go to the next slide, I just want to say, you see, the data path block diagrams can become a little bit too much information to look at in one slide. So what you will see is selectively some may not appear all the time. So for example, if you look at this, which particular instruction is missing from this slide, from this block diagram? There's one instruction that we kind of added a jump, right? Yeah, there's no jump because we are not taking the program counter +4 and we are not shifting it. Earlier we drew it up here, right? Remember that? We drew it up here, but we didn't include that later. So the only reason for that adding and subtracting is so that sometimes things can get a little bit too much to look at, and you know, if it's not necessary in a particular block diagram, you can skip it, right? So it's not being shown. It's not that it's not there. It's there, but it's not being shown. Okay, let's go ahead. Now let's talk about controlling the ALU. So more details about the 2 bits of the ALU op, and then what is the ALU supposed to get? So the ALU control depends on instruction. We are going to define an intermediate set of 2 control bits called ALU op. What are they? They are outputs of, these are output of output of main control unit. So those are intermediate, right? If you see this, ALU op is here, but it is intermediate, right? Because what really matters is what is the input to the ALU. So ALU op is only functioning as an intermediate signal here. Let's go on. So let's try to define what that ALU op code bits need to be for a specific instruction type. So if both the bits are 0, 0, the least significant bit as well as the most significant bit, if they are both 0, then it means that you are performing an add operation meant for load or store word instruction. Because for load and store word instructions, you have to add the base address to the offset. So for those type of instructions alone, you are going to make ALU op code bits, both of them, to be 0. If the least significant bit of ALU op is 1, then you are doing a subtraction which is meant for the branch when equal instruction. Remember, for the branch when equal instruction, you are trying to compare the values of 2 registers, and an easy way to do that without using a comparator is to subtract them. Who does the subtraction? The ALU does the subtraction. So that's why we have this different intermediate signal to indicate to the ALU that, okay, you're not doing a subtraction as an R-type instruction. You're doing this subtraction for the branch when equal instruction. And if that leads to a 0 result, we would appropriately compute the branch address by updating the PC accordingly. Now, when the ALU op code, the most significant bit is 1 and the least significant is 0, then we are going to be looking at the function field that specifies the R-type operation. So this last entry is specifically for R-type instructions, and the other input of the ALU control is going to determine which specific instruction are you doing. Are you doing add or are you doing add U, right? Because the ALU control, apart from ALU op, it also has the function field, which is meaningful for R-type instructions. So if the ALU op is 1, 0, then it would start looking at the function field and then appropriately assert the signal to the ALU. Now, so that's your top table talking about the 3 variations of the ALU opcode. Remember, we are doing this for a limited set of instructions, right? So we are doing this for only 8 instructions. Now, if the MIPS ALU, the main ALU, has the following functions. For example, now we are saying that let us try to add some AND, OR, add, subtract, set on less than. All these instructions. How are you going to differentiate between them? They are all sort of in the same category, right? These are all R-type instructions. So how are we going to determine what the ALU input should be? In other words, what should go on this line to the ALU. So there's an arbitrary assignment for MIPS, which is ALU input is 4 zeros, then you do AND. ALU is 0001, you do OR, and then 0010, you do ADD, and so on. Right? Now, let's try to put it all together in this particular table. What we have here is, all the way to the left, we have the instruction opcode. This is just the mnemonic for that. Load word, store word, branch when equal. Those are the three I-type instructions. And then the rest of the instructions over here are R-type. What would be the ALU Op Code Bits for that? Well, we have just talked about it, right? For example, for load word, you would have 00. For store word, you would have 00. For branch, you would have 01. For all the R-type, you would have 10. So those will be your two opcode bits. This is the instruction operation. So that was the symbol. This is the operation. Load word, store word, and so on. At this point, I think that is self-explanatory. Then we come to the function field. Well, if the first three instructions are I-type, in I-type, there is no function field, right? The function field is only meaningful for the R-type instructions, in which the last 6 bits are associated with function field. But for I-type, those 6 bits, in fact, the last 16 bits are for an immediate address, for an immediate constant or address. So those are don't cares as far as the I-type instructions are concerned. But as soon as you go into the R-type instructions, those will start mattering. What does it have? If you see this, it has you can separate it out into two categories. Let me highlight that in yellow and blue. The first 2 bits in the function field are exactly what you have for the ALU op. And then the rest of the 4 bits are coming from the, to distinguish between add, subtract, and all that. So that is from this table right here. You see that? So if your function field is 100000, you look at the first 2, you know that it's a R-type instruction, and the remaining bits will tell you what exactly what is the desired ALU action. What about the ALU control input for those instructions? So for add, subtract, those are what? Add, subtract. Let's go back and see. Add was this, and then subtract was, so 2 and 6, right? So 2 and 6 go here. 2, and then 6. And then you know based on that same table, you can probably figure out all the others. So let's try to kind of recap, look at it by zooming out, right? So you have the mnemonic over here, bunch of I-type and R-type instructions. Then based on the op field, you would compute the ALU opcode. That will be an input to the ALU control unit, which is also useful to compute the ALU control input, right? So 2 things go into computing the ALU control input. One is this, and the other is this, right? So both combined, you find the ALU control input. But obviously for the I-type instructions, the function field doesn't matter. Those are don't cares. Only the R-type instructions matter. Now you may say, all right, where do I find the function field for add? Where do I get this information from? For the general case, well, you would simply go back and take a look at your MIPS card. And if you take a look at your MIPS card for R-type instruction, you would have an opcode field, and you would also have the function code field. Whatever the function code is, that would be your 6 bits over here. So that is coming from the reference card itself. Then depending on what you're trying to do as far as ALU is concerned, because sometimes you may want to add for the sake of load word, sometimes you may want to add for carrying out the add R type instruction. So they are same add operation, but so to distinguish between the two, you have your function fields, right? That it doesn't matter. Over here it matters. The ALU op different from load word, but for the ALU it is still an add. So this matches that. You guys see that? So this is all the way. These are operations that the ALU is carrying out at this column. Which, so at this point it becomes irrelevant what type of instruction it is. As long as you are adding, you would want your ALU to add. So the ALU control input will be 0010 for add. Now, it looks like we have a truth table, right? So if you tell me the opcode and the function field, I can tell you what the ALU op is going to be. I can tell you what the ALU control input should be. I can tell you all of those because I have a truth table. So each ALU control input, we can find the gates that relate, the input being ALU op and the function field, the two highlighted in blue, and the output being ALU control input. So essentially, let us take a look at a combinational circuit. What is that for? The ALU control, right? So we are trying to build the combinational circuit, for ALU control. There are two inputs highlighted in the blue circles, ALU op and the function field. There's only one output which goes to the ALU, the 4-bit ALU control. It's a truth table, so we should be able to design a combinational circuit for that. We will do that in just a second. Before that, a quick note about PC source. So the setting of the control lines, except for the PC source, is completely determined by the opcode fields. So just for the PC source, we have the main control unit that gives you that PC control, right? But everything else is coming from the instructions, the opcode field, the ALU op, the memory to register, the register destination, mem read, mem write, all of those control lines, the setting or not asserting of those control lines is being determined by the opcode fields, the 6 bits, the 6 most significant bits from the instruction itself. So next question is, what about program counter source? What about PC source? Where is that coming from? So let's take a look at a diagram without that. So that's where it is coming from, right? So the instruction is coming here. It gives you a bunch of control lines. The way PC source is being computed is by ANDing the zero result of the ALU along with the branch control. So depending on whether both of these are 1 or not, you would determine PC source. Different from direct outputs of the main control unit. All right, let's talk about that. Okay, so the table at the bottom here differentiates between instruction types, and it gives you all the outputs of the main control unit. For R-type instruction, what should be the register destination, what should be the ALU source, what should be the memory to register, and so on. Wherever things don't matter, you have a X. Wherever things matter, you either have a 0 or you have a 1. And we can talk about it, talk about these settings at great length. But let's talk about some things that are pretty obvious. So for example, if you look at the branch when equal operation, that's a branching instruction. So only for that, the branch control is 1. For all the other R-type instructions in the load word and store word, your branch output here from the main control unit is 0. When do you do memory write? You do memory write only when you are trying to store a word. So this is 1 only for the store word. When do you do memory read? You only do memory read when you are loading a word. So that's 1 only for that location. How about the ALU source? ALU source is asserted for load word and store word because that is picking up the target address, right? When you add the base address plus the offset. In the other two cases, the ALU source is 0, which is essentially saying whatever the output of the ALU is directly, the ALU source. So ALU source is right here, right? So in two cases, when it is 0, it is read register 2, and for the case of load word and store word, you have the 32-bit extended, that is the ALU source. So we can keep on talking about these settings. The last 4, of course, are the last 2 columns for ALU op are of course coming from the table that we discussed here, right? Load word, store word, you have 0 0. Branch, you have 0 1. All the R type instructions, you have 1 0. So that's kind of going over here. All right. Questions about this? Any concerns about computing a particular control line for R type instruction, load word, store word, branch when equal? Right. So we were talking about building the combinational circuit, right? So we building the combinational circuit that that makes up the main control unit and the ALU control unit. So on the top right, what you have is the main control unit. The inputs to the main control unit are the 6 most significant bits of the instruction. 6 MSBs of instruction, regardless of what type of instruction it is. All instructions have op field. They all have the 6 most significant bits that go there. And then depending on what bits are active and inactive, you would compute all these control outputs. Register destination, ALU source, blah blah blah, all of them, including both the ALU op bits. So let's take an example. Maybe we can take an example of load word just to see if this works or not. Load word instruction has an opcode of 23 in hex. How do I know that? Well, I looked up the MIPS reference sheet. So what is 23 in hex converted into 6-bit binary? So if you convert 23 to binary, you should get 20 plus 3, so 16 plus 4 plus 2 plus 1, right? Let's see. Did we get that? 16 plus 4 plus 2 plus 1. We got 16, 8, 4, 2, 1. Is that right? Let me just check whether opcode, load word opcode is 23. Let me make sure that it is. Let's see here. Going to go all the way down. MIPS green card. Let's see. Jump. No, not jump. Load word. Load word. Yes, 23. All right. So, am I doing this right? Eight 16. Hold on. The most significant bit is going there, right? So this is 1. Did I look up the wrong thing? Oh, that was... You were converting from decimal, yes. Alright. So what is 23 in hex to decimal? Right. The 2 and 3. Right. So I need 6 bits. I can take off the 2 bits. Alright. This makes sense. Thank you for catching that. So I got 10011 in binary, right? So those are my 6 bits. Now, if these are my 6 bits, you see, I can map them over here to 1 0 0 1 1 1 3 zeros 1 1, right? The 3 bits in the middle are getting inverted. At the end, I will get all ones over here. Goes through an AND gate to assert the load word signal. And then if load word is active, ALU source is going to be asserted. Or if store word is active, ALU source is going to be asserted. How do we know that? Well, it is right here. Load word or store word. ALU source has to be active when load word is active or store word is active, right? So this table is essentially determining that network over here. Then the conversion between the opcode into bits is dictating how to make these AND gates. Essentially, which bits to invert and which bits not to invert. An R-type instruction is pretty straightforward, right? All of them have to be a 0 for R-type. So all these inputs are inverted, goes through an AND gate, and that computes your single output, which is used for register destination, has to be active for R-type. Register write has to be active for R-type, and ALU Op 1 has to be active for R-type. So that's your main control unit. Take a look at your 6 most significant bits of the opcode and convert to decimal first, so as to not get worried about why it doesn't make sense. Then after hex to decimal, you convert it into binary, then should be okay. Now let's turn our attention to ALU control block. So this is the ALU control unit. Has two inputs. ALU op, those are the 2 bits coming from main control. And there are 6 least significant bits from the instruction itself. 6 bits, least significant bits from instruction. Now, how do we know which particular operation because there are 4 bits I need, right? I need to have an ALU input. The output of this is ALU input. So if I know the 2 bits from for ALU op and the 6 bits of the function field, do I know the 4 bits of ALU input? Well, let's try to see. If you know the ALU op bits, then you know whether it's a R-type instruction, load word, store word, or branch when equal. And each of these will have a different for the R format, it will have a different function field. Those are all built in over here. So for example, if the ALU op, the least significant bit, goes to the input over here, and it looks like the AND is getting X and X complement, right? So op 3 is 0. Is sort of 0 all the time, right? So that's your most significant bit of ALU input is 0 all the time. Let's check whether that makes sense or not right here. So if you take a look at the most significant bit here, it is 0 all throughout, right? And then you have some logic that controls zeros, the inputs being this and this. So think of it as there is a truth table with 8 inputs, right? 6 of them from here, 2 of them from here. And there are 4 outputs for ALU control input, right? That's the input to the ALU. Depending on how these are laid out, you are essentially figuring out what are these outputs of that combinational circuit. Let's see. For example, for operation 2, which is the next most significant bit of ALU input, it is going to be 1 if ALU op is 1, or if F1, which is, you know, the bit location 1 of the function field, and ALU 1 is 1. And if you look back at your truth table, it will satisfy. So that's how your ALU control block is determined, based on the truth table in which you have 2 inputs for ALU op, 6 inputs for function field, and then you will get 4 bits of ALU input. So it might be confusing about ALU input. So ALU control input, right? So this is essentially referring to where is that? This guy, and it is referring to this line right here. Okay? So those are not data. Those are not operands. That's the ALU control. Okay, let's go over here, and now let's talk about a different thing. The next thing we are going to talk about is the delay through each of those components. So if we try to classify the components that we have been looking at in our block diagrams, you could classify them as memory, or ALU and adders, or register file, and everything else. And the way we are sort of classifying them, the reason why we are classifying them into different types is because the access times, meaning reading and writing times to each of these components, could be different. And it will have a direct impact on the fastest clock rate we can have, highest clock rate we can have. So for memory access, the typical value is about 2 nanoseconds if you want to write to a memory or read from a memory. For ALU add and adders to work through an instruction, you have 2 nanoseconds as the speed. Accessing a register file needs 1 nanosecond. And everything else is so small that you can neglect it. Right. So let's try to look at, for each type of instruction, what are the different components I would need to use. So on the left column over here, you have type, R type, and then a few I type instructions in load word, store word, and branch. You have what are the components being used. You need a fetch component. Fetch meaning instruction fetch. Right, this is instruction fetch. Yes, of course, I need to do instruction fetch for all of them. So that step is going to be there regardless. You need to access the register file. It looks like for all the instructions, you do need to access the register file. That is register access. Do you need to use the ALU? Looks like you do need to use the ALU for all of them. For R-type instructions, you are carrying out add or subtract or and whatnot. For load word, you are doing an addition. For store word, you are doing an addition. For branch, you are doing a subtraction. After that, the result of your R-type instruction, say example add, you would need to write back to the register file. So you need to access the register again at the end. So you can think of it as this is sort of time, right? Increasing time. So you're first doing this, then doing this, then doing this, then doing this. But as soon as you write to the register file, the R-type instruction is done. As far as load word is concerned, need to do instruction fetch, need to access the registers, need to add to compute the target address. Then you need to do a memory access because you're reading the memory now. And then you also need to write it back to the register file. The register access is also required. As far as store word is concerned, instruction fetch, yes. Register access, yes. ALU for addition of to get the target address, yes. Then just write to memory. So maybe I can do this. I'm reading here, I'm writing here. Don't need to do any register write here. For branch, it turns out you only need to do an instruction fetch, then you need to do the register access, then ALU, when you do the subtraction, tells you whether there is a 0 result or not. Done. You don't need to do anything after that. Or in other words, you can neglect the time taken by other components after that. So if this is the case, let us try to see what is the delay analysis, meaning if an instruction is being executed and say a certain component has 2 inputs, you would want both the inputs to be available at the right time in order for that component to actually work on those numbers. So let's do a delay analysis for R-type instruction, then load word, store word, and we will also do a branch when equal. For the sake of reference, we have this table over here, which is sort of a copy of the table that we listed earlier. Component on one column and their respective delays on the other column. So when you're working through an R-type instruction, you start with instruction fetch. Instruction fetch happens in the instruction memory, which requires, so that's your instruction fetch, right? So let's talk about where is this happening. This guy is happening right here. Instruction fetch is process of reading the instruction memory at the program counter location for the next instruction to be executed. Then there is register access. Who does the register access? Well, that points to the register file. One nanosecond speed of that register file, register access. The first time you're doing the access is for reading. After you do the register access, you read two numbers. Those will go through an R-type instruction, add, subtract, and whatnot. That particular instruction will be carried out by the ALU. ALU and the adders actually have a speed of 2 nanoseconds. So that's happening over here. So for ALU, I can draw an arrow right there. Perform the instruction. As soon as your result is available, you do not do a memory access. You simply do a register file access. Now you are doing a write. So even this guy is happening over here. But in this case, you're doing a write. So what would be the total time taken for an R-type instruction to get executed if my assumption is that memory access takes 2 nanoseconds, ALU and adders operate at 2 nanoseconds, register file access takes 1 nanosecond, and all the others are neglected. So you've got 2, then 1, then 2, and then another 1 at the end, right? So you got 6 nanoseconds as the time it takes to execute an R-type instruction. Questions here? I can probably even write read over here because I'm just reading the instruction. All right. A lot of things are going to be similar, but a few things are going to be different for the delay analysis of load word instruction. Because for load word instruction, you do an instruction fetch, you do register access, you do ALU to compute the target address, then you need to do a memory access followed by register write. So you start with memory fetch, instruction fetch takes 2 nanoseconds. You got that, the first number. Then you need to do a register access. Read register 1. That needs 1 nanosecond. Then you need ALU to add the offset to the base address. That needs 2 nanoseconds. Then you need memory access because you want to read the memory because you're loading the word into a register. So reading needs 2 nanoseconds. Then you need to write it to a register file, to one of the register, because you need to load the word from the memory to the register. So write. So you got 2 plus 1 plus 2 plus 2 plus 1 at the end to write. So you got 8 nanoseconds as the time it takes to execute a load word instruction. How about the store word instruction? Well, for store word, you're taking things from the register file and then storing them into the memory. So in this case, you do an instruction fetch, yes, 2 nanoseconds. Then you do a read register access, yes, you have to read a register. Which one? Base register, right? So the base address is going to be at a register, right? So that's 1 nanosecond it takes for you to read that. Then you need to add what to what? You need to add the base address from a register to the 32-bit sign extended offset. Okay, so that happened there, 2 nanoseconds for ALU incorporated here. Then you need to write to the memory. So memory access takes 2 nanoseconds. So you've got 2 nanoseconds over there. Done. 7 nanoseconds in total. So far you have seen 8 for load word, 6 for R type. So it looks like depending on the type of the instruction, the time it takes is different. Now let's take a look at a slightly different instruction, because this is going to take like a very short amount of time, because the register access is not there, memory access is not there at the end. So what you have is a branch instruction. You do a fetch at the beginning. Yes, you do a fetch, 2 nanoseconds. But now you actually have 2 paths to consider. In the previous one, you didn't need to consider the other path, but now you do have to consider the other path, because depending on whether you are branching or not, you will either pick one address versus the other address. You will either pick the branching address versus PC plus 4. Both inputs should be present in order for that adder to work. So things, when they arrive, they need to arrive over here, that adder, at the same time. What is that adder used for as far as branch when equal instruction is concerned? This is add. Can someone tell me why we need this adder here? For getting the new PC value. Okay, so to get the new PC value, in one case it could be PC plus 4. In other case it could be PC plus 4 plus the target address, right? Or branch address. So this adder is being used to compute that guy. PC plus 4 plus a new address that you have to incorporate in case you have to jump to an instruction. Yes. So that adder is to do this, right? Is specifically to do this. Because this was being done right here. All right, so when you have to do this PC plus 4 plus branch address, one of the inputs to this adder is branch address, the other input is PC plus 4. Both have to be present in order for that addition to take place. Now let's talk about, depending on how the branch instruction flow control happens, whether that is going to be the case or not. Well, let's start. Instruction fetch needs 2 nanoseconds. Okay, so that's your fetch. The adder, the first adder, happened in parallel with the 2 nanoseconds here. Adder needs 2 nanoseconds. Instruction fetch needs 2 nanoseconds. So those, both of them happened at the same time. So right away your one of the inputs is ready, but we cannot add because the next address is not ready yet. So what are we going to do? We are going to have to see the result of the branch instruction. Are we taking the branch or not? How do we do that? We have to first go read registers, bring them to the ALU, subtract them, and if the result is a 0 from there and the branch signal is asserted, then you can say, all right, fine, now I can add the branch instruction and then go forward based on that. So one path is fast, the other path is slow. The other path is 2 plus 1 plus 2, and then things go back, right? So you're done. 2 plus 1 plus 2, done. So that's fetch, register, ALU, 2 plus 1 plus 1. And in the other path, you have 2, and then data has to be there, right? So that's 2 and then 2 right here. There is a discrepancy. So what you would do is, you would not take the shortest time, but because you have to wait over here in order for the other side to be available, you would consider the longest path, which is 2 plus 1 plus 2. So 5 nanoseconds for branch instruction. No need to do memory access, no need to do register write, register file writing. Now if I lay out the time used by each instruction, for R-type I computed that 6 nanoseconds, load word 8, store word 7, and branch 5 nanoseconds. A couple of things I would like you guys to note from here. One, things that were with respect to memory, when you had to read things from memory or write things to memory, it actually took you longer than things that did not require memory access. For example, R-type and branch type. So it looks like if you want to do memory access, then things become a little bit slower. So that's the first thing that I want you guys to take away. Next, because load word is taking 8 nanoseconds, and I am trying to look at a single processor working on this instruction, my max instruction per cycle, max IPC, is 1 for single core. In other words, I'm going to have to make my overall clock cycle, which is 1 over the clock rate, to correspond to the largest one of these, which is 8 nanoseconds. So that limits the clock rate that I can use for these instructions to be carried out. I cannot reduce clock rate as low as possible. No, I can't do that. So now, because there is a discrepancy, there is another consequence of this, which is if you end with a branch instruction, it ends 3 nanoseconds before a load word instruction could finish, right? So branch instruction ends in 5, load word ends in 8. So if there was a branch and then you are limiting things to 8, then you have 3 nanoseconds of idle time after each branch instruction, which is not very ideal, because that is essentially leaving your resources not being used. Why does this matter? This matters because the next time we meet, we will start talking about pipelining. Pipelining is a very elegant concept in which you are trying to make sure that almost all your resources are being used all the time. What I mean by that is, you see, you have an instruction fetch, register file here, memory here, ALU here. So there are bunch of hardware, right? But if you are looking at only one instruction going through, then only one instruction uses this, and then after it is done, the next instruction comes in. So what about using the instruction, the memory or the fetch cycle for a different instruction once the first one is done, right? So that's kind of leading into pipelining. And this sort of limitation plays a crucial role when we start talking about pipelining, because there is a difference in terms of time it takes to execute each instruction. All right, so this also leads to the conclusion at the bottom of the slide here, which is this waste would be much greater if you start including more and more instructions. For example, floating point instructions will take a lot longer than the instructions that we have been looking at the smaller set. So the discrepancy, the difference between the fastest and the slowest instruction will be a little bit more pronounced in that case. All right, I think you guys are ready for the activity. Please go to Piazza, grab the activity from there, work on it, and please submit it on Gradescope by midnight tonight. I'm going to stop in recording.